Hello Math Studies students and welcome to your online lesson. Today we'll be using parabolic graphs, or graphs of parabolas, to identify the quadratic function and axis of symmetry that would have been used to create that actual graph. So we're sort of working backwards, starting with the graph and then figuring out the function and other attributes. We will know we are successful when we can efficiently interpret and graph quadratic functions. Quick reminder that a quadratic function must have an x squared in order to be a quadratic. The a term, or the a coefficient, is usually in front of x squared, b is in front of x, and c is our constant. When we have a quadratic function, we usually use a y equals or an f of x equals, but it still has that characteristic x squared as the largest power of our variable. Also worth pointing out that when we graph a quadratic, we end up with a parabola. A parabola is sort of U-shaped, kind of V-shaped, doesn't have a sharp point, but it does still have a vertex, just like an angle in geometry. And through that vertex, we have this line known as our axis of symmetry. And parabolas are symmetrical, meaning that everything on the right can be reflected over the axis of symmetry to find a corresponding point on the left, and vice versa. Something else I want to point out is that we have solutions to our quadratics that occur when the graph of that quadratic, the parabola, cross the x-axis. And for this particular one, which opens upwards, there are two spots where it crosses the x-axis. Each of those spots, you will notice, is symmetrical around this axis of symmetry that goes right through the vertex. So the distance from my solution here on the right, or my zero, or my x-intercept, is exactly the same distance that we have here. And so another way to say that is that the axis of symmetry is right in the middle of those two solutions, or x-intercepts. So how do we find something that is right in the middle of two other values? Well, just like when we calculate grades or anything along those lines, we use average, or in this case mean, where we would add those values together and divide. And you'll be seeing that on a later slide when we actually need to find that axis of symmetry from our graph. Last thing I want to say as review is when we have an a term that is greater than 0, and again, a is the coefficient of x squared, we have a graph that opens upwards, meaning that it has a minimum and the graph extends infinitely positive on the y-axis. If we have an a term that is less than 0, meaning a negative a term, then our graph will open downward and we'll have a maximum for our vertex. All right, so using these old skills and then a few new that we'll pick up along the way, we're going to look at a couple examples here now. So for the following graph, write down the quadratic function and the equation of the axis of symmetry. Well, I'm going to sort of work backwards here a little bit. Let's first just get the easy thing out of the way, and then for me, I think that's the axis of symmetry. So like I was talking about a couple slides back, we have two spots where our graph crosses the x-axis, or two x-intercepts, which means we have two solutions to this, -1 and 3. Our vertex, which occurs somewhere around here, is going to have an axis of symmetry that goes right through it. And those two solutions, the -1 and the 3, should be symmetrical around that axis of symmetry, meaning that the axis of symmetry goes through the middle, or the midpoint, of those two values. So how do we find the middle of -1 and 3? Well, I take the -1 and the 3, I add them together and divide by 2. What is that called? That's called finding the mean, or the average of something. So -1 plus 3 gives me 2, and I divide by 2 to end up with 1. So is 1 an equation of the axis of symmetry? No, 1 is just the x value that would be smack dab in between those two solutions. Now I want to write the actual equation. So for an equation of an axis of symmetry, I always start with x equals for a vertical line, and here we have x equals 1. And we can see that that sort of seems reasonable, because if this is a 1 over here and I move another unit over, this would be roughly a 2 here, and then here I have 3. So even with my crude sort of sketch that I'm doing right on top of the graph, we can see that that seems reasonable. All right, so that's the equation of the axis of symmetry. Now we're going to move on to actually finding the equation of our quadratic function. And this will be a little bit more involved, and we'll look at a second example where we'll go maybe just a little bit faster after we've sort of established what we need to do here first. Well, one thing I just want to point out is that when you have a factored quadratic, like let's just say I had x plus 1 times x minus 2. the actual solutions of this quadratic, to find them, I set each of my factors equal to 0. So I'd have x plus 1 equals 0, and I'd have x minus 2 equals 0. I'd solve them, and for this one, I would end up with x equals negative 1, and here I would add 2 to both sides, and I'd end up with x equals positive 2. Now, look at my answers. I had a negative 1 here, and yet in the binomial, I had a positive 1. The sign switched. So in my actual factor, my binomial, I had a different sign, in fact, the opposite sign of what I had as my solution. And the same thing's true over here. I have a positive 2 as my other solution, and yet when it was in the binomial, the sign was the opposite. So looking back at our function that we have here, or our parabola, we have two solutions, negative 1 and a positive 3. But when I write them in the binomial form, I need to make sure that I am switching their signs. So I am going to take my two binomials, x and x, and I'm essentially going to do the opposite of whatever said. So for this first one, I have this negative 1 as my first solution. But I'm going to write minus negative 1, or the opposite of negative 1, which is to say x plus 1. And then I have this other value here, which is x plus 3, but I'm going to subtract that. So I have x minus 3. And that's the beginning of writing the quadratic equation, or quadratic function. I just need to know what those two values are. I also want to make it an actual function, so I'm going to put a y equals on either side. I can have y equals in the front, y equals in the back. And then the last thing I need to worry about is there's a possible a term. Something that's multiplying the whole thing out front, which is stretching it out or shrinking it or flipping the graph or something along those lines. Well, speaking of flipping the graph, we do have a maximum right now, which means that our a term must be negative. A must be less than 0. So that's something to keep in mind. But how do I know exactly what this a value is? So the first thing I'm going to look at is, do I have a point anywhere that I actually know some values for? I have a couple points, actually. I've got these two values right here, which have x values of negative 1 and 3, but then have y values of 0. The problem is, if I plug those in, I will end up with a 0, and everything will cancel out. So you don't want to use x-intercepts. But there is one other value that I have. I have this value right here, which it's labeled as a 3, meaning the y is 3. But there's also an x value that goes with it. And since it's a y-intercept, the x is 0. So right there, I have an ordered pair, 0, 3. Now, what does that ordered pair really mean? That means that when x is 0, or when I plug in a 0, I should end up getting a 3 out. So what I'm going to do now is go back to what my binomials that I've written over here and start plugging some things in. I still don't know what a is, but I know that if I plug in a 0 for x, so 0 plus 1, and then 0 minus 3, I'm supposed to end up with a 3 for y. So I'm going to simplify now. Over here, I have 0 plus 1, which is just 1 times a. And then over here, I have 0 minus 3, which is just a negative 3. And when I get my answer, I have 3 out at the end. So now I'm going to simplify. A times 1 times negative 3. Well, a times 1 is just a. It's an identity. And a times negative 3 would give me negative 3a equals 3. Divide both sides by negative 3. And I get a equals negative 1. So let's go back to my actual quadratic function that I have here. I'm a little bit out of room, so I'm going to move over to the left side of the board. And so I had a negative 1 times x plus 1 times x minus 3 equals y. And that's my quadratic. Now, if they want me to put it in the form of ax squared plus bx plus c, I can certainly do that by distributing and expanding. So if I do a little bit of FOIL here, I would end up with x times negative 3, 1 times x, 1 times negative 3. And so x times x gives me x squared. X times negative 3 gives me negative 3x. I have 1 times x, which gives me x. And then finally 1 times negative 3, which gives me negative 3. But all of that is still getting multiplied by a negative 1, and it all equals y. So for my final equation, I would have negative x squared plus 3x. Oh, sorry, if I combine these two, I'll have a negative 3x plus an x, so that's negative 2x. But when I multiply by the negative 1, I have a positive 2x. And then finally, a plus 3 at the end equals y. Now, if I lost anyone here on this final thing, again, you would only have to do this if they said to put it in the ax squared plus bx plus c form. I really had a quadratic all the way over here when I wrote it in red. It was just a factored quadratic. And so you don't need to do those extra steps unless they ask. And just a reminder, why did all my signs change? Because of this negative 1 that we had all along the way there. All right, so now let's do another one. I know that that might have been a little bit confusing getting started, but we will look at another example and hopefully make some connections as we do this one. So we have a little bit of different information here. This time they only give me one solution to the problem. They give me an x-intercept of 1. They don't tell me what the y-intercept is, and there's no scale to figure it out. And there's no other x value given. It looks like it's about 3, but they don't tell me that. So the instructions say, for the following graph, write down the quadratic function, and again, the equation of the axis of symmetry. Also, once again, I'm going to work backwards. I know where the equation of the axis of symmetry should be. It should go right through the vertex. It's a vertical line. Well, I already know the coordinates of the vertex. It's 2, negative 4. So my x value is 2, which means that my equation of my axis of symmetry is x equals 2. There's a vertical line that goes through every value where x equals 2. All right, so that would be my equation of my axis of symmetry. Now on to the more meaty stuff, writing the equation of our quadratic function. Well, once again, I am going to use my solutions here. I have a x minus, or the opposite of whatever values they've given me. Well, they already gave me a 1, so I'll have x minus 1. The problem is I don't have this other value. I don't know what it is. I need to figure that out. Luckily, I know that I have this axis of symmetry here. And my axis of symmetry we already labeled as x equals 2. Well, how far away is 1 from 2? Distance. Well, you can subtract. 2 minus 1 gives me 1. So they are 1 away from each other. So 1 to the left of this 2 gives me a positive 1. And 1 to the right of this 2 would give me a positive 3. So I do know, in fact, now, because of my axis of symmetry, which means that everything is symmetrical to the left and to the right, same distance away, that we must have another solution at positive x equals positive 3. But when I put it in my binomials, I'm switching the sign. So I have x minus 3. We want to set this all equal to y, and we want to throw an a out front. We're almost done, except again, I still need to figure out what a is. In order to figure out a, I need to plug in a point for both my x's and for my y. Well, last time we had used the point at the y-intercept. We don't have that point this time. And again, we can't use the points of our x-intercepts because if you do those, you will end up with everything canceling out and equaling 0, which we already know is the case. So that's going to not help us out either. But we have one last point right here at my vertex where x is 2 and y is negative 4. So that's what I'm going to plug in. Bring down your a. My x is 2, so 2 minus 1. 2 again, 2 minus 3. And then finally equals my y, which in this case is negative 4. I'll just write that 2 a little bit neater. So I'm going to simplify this. So I'll still have my a. 2 minus 1 gives me 1. 2 minus 3 gives me negative 1. And then I have a negative 4 over here. Well, 1 times negative 1 gives me negative 1. So my a is just going to be negative 1a, or negative a. And then bring equal sign, negative 4. They're both negative, so you can cancel out those negatives or divide by a negative 1 to get rid of those. And then you end up with a equals 4. So that is the a value. So now I can go back to my quadratic and write it all out. So I have 4 as my a times x minus 1 times x minus 3 equals y. Again, if I wanted to, I could do FOIL here and expand all this, put it in the form of ax squared plus bx plus c, and then distribute a 4 to all those terms as well. I could put the y out front if I wanted, but I already have a quadratic, and that's all that it was asking me for. I can put this in various forms. I could graph it, throw it in my calculator, all these different things, but that's what we are looking for. All right, so that was graphing quadratics, or starting with graphs of quadratics, and then using those graphs to actually write the equations of our quadratic functions, as well as finding the equations of our axis of symmetry. Till next time.